Hello, everyone. Welcome to this session of RoboLaunch. Today, it's my pleasure to introduce Professor Stelian Coros. Stelian is an assistant professor of computer science at ETH Zurich, where he leads the Computational Robotics Lab. Through fundamental advances in numerical simulation and motion control algorithms, his research bridges the fields of robotics, visual computing, and computational fabrication. Applications of his work range from studying the principles of dexterous manipulation and legged locomotion to computation-driven design for new breeds of bioinspired robots. He is the recipient of the Alain Fournier PhD Dissertation Award, an Intel Early Career Faculty Award, a Research Initiation Award by the U.S. National Science Foundation, and in 2020, he was awarded an ERC Consolidation Grant. Prior to joining ETH Zurich, he was an assistant professor in the Robotics Institute at Carnegie Mellon University. He received his PhD in computer science from the University of British Columbia in 2011. So, without further ado, I'll hand it over to Professor Stelian.
All right, thank you for the introduction. Let me share the screen. All right. Let me see. Do you see the screen right now?
Yes.
All right, perfect. Okay. So I wanted to give a brief overview of some of the work that we do in my lab here at ETH Zurich. And the title of this talk is called Physics-Based Modeling and the Quest for Intelligent Robots. All right. Now, I don't know if many of you know this, but the term robot was first coined a little more than 100 years ago in 1921 in a play called Rossum's Universal Robots. Oh, and ever since this first depiction of robots, we have seen lots of examples in science fiction of intelligent robots. Now, unfortunately, in sort of most of these science fiction depictions, robots sort of revolt against mankind and bad things happen. And just to be clear, my dream of intelligent robots is not this, but rather we think of intelligence using this definition, which basically has to do with the dynamics of interactions with the world. So in other words, I would like to see machines that are able to interact with all sorts of physical objects as dexterously as we do. And that will, I think, bring about the dawn of a new technological revolution. And we're going to have these intelligent machines that are able to support us with all sorts of tasks at home and at work. So this is kind of the future that I imagine and that we're working towards. And if I had to sort of summarize the work that we do, we kind of split it up into three different pillars. First of all, we do a lot of work in physics-based simulation. And here, the overarching goal is to use these new simulation models to enable machines to understand how physical objects move and deform, to have the same kind of innate understanding that we do, whether it is that we are I don't know, folding a t-shirt or cooking our dinner, we always have an understanding of how the objects we interact with will behave. And using this understanding, we are able to plan and execute motions. And here in the simulation models that we're developing, I always am interested in understanding how to make the most of the information that simulation models give us. So building on these simulation models that we're building, we develop all sorts of new algorithms for motion planning, for control, and also for computation or algorithmic design for new types of robotic systems. And we also use data as much as possible to reduce the computational burden, to bridge the reality gap, to enable learning by demonstration, and so on and so forth. So it's this fusion of simulation, algorithms, and data that we call computational robotics. Now, in terms of the types of problems in robotics that we look at, we classify these more or less in four different areas. One is locomotion or mobility. And here, the overarching goal is to make robots that are able to go wherever people go. And so for this purpose, we study all sorts of mobile platforms, whether it's legged robots or wheeled robots or hybrids, as we see here in this example. We always try to figure out how to make these robots as agile as possible. And now increasingly, we're looking at mobile manipulation problems. So we want robots that are not just walking places, but are also able to start interacting with objects around them. Speaking of manipulation, we have a dedicated focus in this area of dexterous manipulation. And so here the goal is to make robots that are as skilled as people are. Hopefully we get there at some point. And in my group, we focus a lot on agility and also manipulation of non-rigid objects. So we see lots of examples here. This is a dynamic behavior. This is another one. This is an example of interaction with a deformable object. So this is these are snapshots of the type of research that we do. And also we're trying to figure out how to create robots that are able to execute long-term motion plans. All right. We also have research in this area of robotic materials, and here computational design or algorithm-driven design is very important. So here we're inspired by new capabilities that are enabled by digital fabrication technologies that allow us to create entirely new types of mechanical systems. Compliance is kind of one of the defining traits of the systems that we study. And in this area, the space of design possibilities is very large, and typical engineering approaches that rely on creating a prototype, fabricating it, testing it, and then figuring out how to improve it, they no longer scale when basically you have access to, thousands of design parameters. And last but not least, we want to create robots that operate alongside humans, or they interact with humans. And so for this reason, human-centered robotics is also a key focus area for us, trying to figure out how to do very fast motion planning, enable intuitive teleoperation, as we see here. And the overarching goal here is to try to figure out in the future, where robots will be all around us, how do we communicate with them, for example, using new mixed reality technologies? How do we share our work with them? How do we decompose it into the tasks that people are good at and robots are good at, and how to formalize that entire process? All right. So in all of these different areas, physics-based modeling is a key component of the work that we do. And the reason why I like physics-based modeling is because if you do it properly, you're able to use simulation environments as a digital twin of the physical world. And within these digital twins, robots can figure out how to do all sorts of tasks that we'd like them to do in the real world. But because it's a simulation environment, everything is safe. If a robot was to drop an object, well, nothing breaks. You can just restart the simulation. And if you do this properly, then once a robot has fine-tuned its skills in the digital world, then those skills will hopefully transfer over to the physical world. So I'll show you very briefly how we make use of simulation models to try to make robots more intelligent. And for this, I want to talk about a new class of simulation models that we've been working on, which is called differentiable simulation. So I'll tell you what that means without going too deep into technical details. So simulation models are usually employed to solve forward problems. What this means is that you create a simulation environment. So here we have a beach volleyball. You might give it some kind of initial conditions. In this case, it would be the initial velocity and the position in the world. And then by running a simulation rollout, if you want to call it that, then the simulation model will just predict how this object will evolve over time, right? So you might get a simulation result that looks something like this. And if the simulation model is advanced enough, then you can model this ball as a deformable object. Hopefully, it's also fast enough. So if you change the initial conditions, right? If you change, for example, the initial velocity of this beach ball, then very quickly you'll just get another result, right? So again, it's just this is an example of the forward problem. Okay, what we want to use these simulation models for is inverse problems. So in this type of inverse problem, what you would say is, I would like this beach volleyball to end up at this location that's highlighted here in the world. And the question that you would ask an inverse simulator is, what should be the initial conditions, the initial velocity and spin, for example, such that after a certain amount of time, this beach volleyball ends up exactly where I want it to end up. And if you formulate the simulation model properly, then this kind of inverse problem is solved automatically. So in this case, the computer figures out the optimal velocity and spin such that after the ball bounces around in this virtual environment, it ends up exactly in the right place. Now, this is a relatively simple example. We're just talking about a beach volleyball, but here's another example that kind of shows the power of this type of approach. So I had one of my students create this robot. It's made almost entirely out of foam. So it's very soft. What we see here is basically the body of the robot. That's the white foam. And there are 4 motors on top. And these motors basically can pull or push, can just pull a cable that's routed through the legs of these robots. So by pulling on different cables, you can essentially activate the motion of the legs. Now here, we just showed that it's an entirely soft system. So the only rigid structure is the supports for the actuators, for the motors that we see on top. And we can model this robot in simulation. And now using this inverse simulation model, what we ask it for is the input contractions of the cables that will make this soft robot move forward. So this is now kind of the result of the optimization. This all happens automatically. And here is the robot, the soft robot, that figured out how to coordinate all of its motors such that it can move forward. So this is basically now an entirely soft robot that figured out how to walk entirely on its own. And again, it uses the same type of differentiable simulator that we saw earlier for the beach volleyball example. So I wanted to go only a little bit into details to explain more how this works. So in a traditional simulation environment, we always have the description of the scene, so what kind of objects are we interacting? What's the environment that these objects are going to be living in? But we also have input parameters, right? So these can be initial velocities, there can be trajectories of muscle contractions for the previous robot. They can even be material parameters such as Young's modulus, so basically how stiff the ball is, or Poisson ratio, all sorts of parameters that are input into the simulation. And once we have these input parameters, we run the forward problem and we obtain some kind of trajectory like this. Now, you always have to discretize your simulation trajectory in time. So what that means is that you're really just predicting the position or the configuration of the objects you're simulating at specific moments in time. So we're going to call this x1 for the first moment in time, x2 for the second moment in time, and so on and so forth. And a traditional simulation environment will output this x of p. So basically the trajectory of the object over time as a function of the input parameters. Now, for a control problem like the ones I've showed, what you also want is a way of specifying an objective. So, what do you want the final configuration in your simulation to look like? For the beach volleyball example, or for this example here, this objective can be very simple. It can just measure, for example, the distance between the position of the object at the last moment in time and its target location, right? So it's a very simple sort of objective. And if you are trying to solve this control problem as an optimization problem, then what you need to do is compute at least gradients of this objective. Now, if you do the chain rule here, what you obtain is an expression that looks like this. So there are some partial derivatives, there are some total derivatives. Hopefully you remember the difference between them. Partial derivatives are all very easy to compute. The tricky part here is this term. So this term, we're going to call it a Jacobian, and it tells us how a change in the input parameters will affect the trajectory that we compute through simulation. So here is a visualization of what this Jacobian encodes. So I just show you what happens here as you wiggle the input velocity. You see here in the frame, in the mesh sort of visualization, this is basically what this Jacobian encodes, right? How will the entire simulation change if you're changing some of the input parameters for the simulation? So you can see it predicts how the ball will bounce higher, or it's going to move further or closer to the initial position as a function of the initial velocity. So these simulation derivatives are very important, and this is what a differentiable simulation outputs. Not only the trajectory that you computed through forward time stepping, but also these derivatives. So I don't want to go into details on how we compute these derivatives. It's a little bit involved, but if you're interested, there are papers on our publication website where you can find all of the details. All right, so essentially, if you have a differentiable simulator, you can compute now gradients of whatever control objective you might have, and then you can run standard gradient-based optimization methods like gradient descent or LBFGS, or even higher order methods, Newton-Raphson, for example, or Gauss-Newton. And together with a line search mechanism, you can get very reliable convergence to a local minimum of this objective. All right, very good. So this is a quick overview of sort of the fundamental inner workings of a differentiable simulator. And now I just wanted to walk you through some of the use cases that we have been exploring in our lab that basically all build on these differentiable simulators that we've been formulating. So here, what we have a lot of flexibility with is what we choose in terms of optimization criterions and in terms of decision variables. So perhaps the most straightforward option is to have simple motion goals, like we've seen in the case of the ball, just have a target for the end of the simulation trajectory. And if the decision variables are control parameters, then this corresponds to whole body control problems or model predictive control or trajectory optimization. So these are all sort of very standard techniques, but now we can build them on top of a differentiable simulator. And I'll just show you some of the work that we've done in this space. So one application that I'm very excited about is robots that are increasingly more bioinspired. And what I mean by this is that they start to approach the mechanical complexity that we see in nature. And in nature, animals, of course, they have an internal rigid skeleton, but also a lot of compliant body parts, whether it's the feet or the ligaments between the bones, or even the muscles themselves that are relatively soft springs, if you want to think about them this way. This is basically one of the defining characteristics of living creatures. And I would really like to see robots that are more organic in their mechanical design. But as soon as they become more organic, they're also much more difficult to model and control with existing methods. And so here we've taken some of the first steps to show that differentiable simulators can be a really good tool that we have at our disposal for these problems. So what I wanted to show here is basically what happens if you do trajectory optimization using a standard model, but then you apply it to a robot that is somewhat soft, has a bunch of sources of compliance. This is the motion that was planned, but now when you actually execute it on the robot, as we see on the left, because the compliance wasn't taken into account, the robot will just not perform in the right way. And on the right here, we see what happens if you use our differentiable simulator. Now, this is an example also with soft feet. It's able to account for all of these sources of compliance and generate motions that embrace compliance rather than sort of just treat it as a necessary evil that's there in every mechanical design. So for locomotion, I think that there is a lot of opportunity for such a model, but also for manipulation. And that's probably an even bigger topic, given that most of the objects that we interact with on a daily basis are actually compliant, they're soft. So we also need the same type of methodology in order to teach robots how to do the sort of things that we do so easily every day of our lives. You know, how do you cook breakfast? How do you make your bed? Those sorts of things. And I'll just show you an example of a sort of almost manipulation example. It's very early on. What we have here is a mass spring system, you know, a very crude approximation of a towel, for example. And what we will see here in this captured video of our system is basically the yellow points here are just the target. So they specify the configuration of this towel sometime in the future. And the control points are the two corners, which you see here using blue dots, that basically would tell a robot where to pick up the towel and what to do with these picked points. And so as you can see, this differentiable simulator is actually quite useful in coming up with the trajectories for the control points that make this simulated object follow some relatively well-specified intermediate and final configuration. And again, all of this happens fully automatically. Here's another example. It's a little bit more complicated. This is a Yumi robot from ABB, a dual-arm robot, and it's holding in its grippers a sheet of flexible foam in this example. And what we asked it to do is figure out how to control its hands so that it starts to lay this foam sheet flat on the table that's in front of it. So here are the results that come up in simulation. You see that there's some anticipatory behavior, really leveraging the dynamics of these systems. And then they, as a result of the physics, they end up starting to lie flat on the table. And now we take these actions that were discovered in simulation, and we have our robot execute them while holding a similar piece of sheet of foam. And here are the results. So basically, it shows that these simulation models have quite a good predictive capability that can be used for motion planning, and then it allows robots to perform the sim to real step in order to really interact with physical objects. So I mentioned earlier on in the talk that so our long-term goal is to have human-level dexterity. This is an example from a sorting or distribution center from Amazon, and it shows you how people currently do these relatively simple tasks, you know, just making sure that the packages have the right orientation on the conveyor belts and that they go in the right path. You see, it's very dynamic behavior, lots of dual-handed manipulation behaviors, very dynamic also. And I think if we look at how the person is doing processing of these boxes and we see how a robot is doing it, we see that there is a pretty fundamental difference, right? So most robots today that are sort of used for real-world applications, they do this very simple pick and place. They always pick from the top and are just able to pick up the object and place it somewhere else. This is sort of one of the types of limitations that we would like to overcome. And one of our early examples in this is sort of this very dynamic tossing behavior. It approaches maybe a little bit what we see this human worker doing in the video on the left here. All right, so these are sort of maybe some of the main types of problems that we want robots to solve, but we don't have to stop here. If instead of control parameters, you know, so joint angle trajectories or joint torques, what we optimize over is policy parameters. So you can imagine here that you have a neural network with tons of parameters that control the mapping between inputs and outputs. If we take exactly these parameters and we optimize for as a function of or using our differentiable simulator, then we can use this kind of system for self-supervised learning or policy optimization, which I think is very exciting. So here is a simple example of a test that we made. What we did here is we had a neural network that encodes a policy, right? So a policy is a mapping between states and actions. Now, the actions that are predicted by the policy are fed into this differentiable simulator, which is treated as a specialized layer in an even bigger neural network. The simulator outputs a motion trajectory that corresponds to that set of actions that the policy output, and then we can formulate the loss directly on this output of the simulator. And if we train this kind of big neural network all at once, then we're able to solve the self-supervised learning problem. So the policy is learned automatically, just using the loss as a guiding objective. So here is a simple example where we use this. What we have here, you're going to see in a second, is a robot that plays a beer pong inspired game. So in beer pong, I've never played myself, so I don't know, but my students told me, you have a ping pong, you have a whole bunch of cups filled with maybe an adult beverage or something like that. And the goal is to throw the ping pong ball such that it bounces once and then lands in a cup. So you can solve any instance of this problem using the differentiable simulator. But what we wanted to do is basically have a pre-computation step where the policy learns wherever this target would be placed inside of the red boundary, the policy that's learned should already figure out the optimal way to toss the ping pong ball. So in simulation, we did a lot of samples of where the cup could be in this domain. We trained the policy using the architecture that I showed on the previous slide. And the result here is that once you have the robot kind of see where the cup is, it can immediately use the pre-computation that we had before to figure out what the result of the policy is, and then it bounces the ball, which then, in the cases that we've seen here, directly falls into the cup. So it doesn't have to solve these inverse problems at runtime because it already learned the solution space for them. And there's actually a lot to be said on this topic. One of the reasons why I like it so much is because it really builds a bridge between traditional trajectory optimization and sort of policy optimization. So basically in trajectory optimization, what we want is to compute the optimal actions that minimize an objective. And for policy optimization, or the self-supervised learning step that I showed before, we have the same type of objective, but now it's integrated over the space of problems that we're interested in. And what we're solving for is not directly the actions themselves, but rather the parameters of the policy that will output appropriate sort of problem-dependent actions. And there's a lot to be said here in terms of how you formulate this policy optimization process such that the policy that you learn is as effective as possible. So we have a few papers on this that you can take a look at if you're interested. All right. Okay, so we can optimize over control parameters. We can optimize over policy parameters. Now we can also, of course, directly optimize over model parameters. So I'll show you what I mean by this, but yeah, I'll show you maybe with an example so that it's most clear to understand. And if once you do this, you can solve what we call computational design problems. Okay, so here's an example. We have a robot. We had an engineer sort of design and build it. It's a quadrupedal robot. And once this design was finalized, we figured out how much weight we can put on top of the robot such that it can still walk without saturating the limits of the actuators. All right, so this is the motion that is optimized for this particular robot. So now this is basically just at the limit of what it can carry. And now we ask the question, well, can we optimize the mechanical design of this robot, in particular the dimensions of the limbs, such that with the same motors, it is able to use less torques while it carries this payload? So here is the optimization process where we're just visualizing the way in which the design of the robot changes. And here it is. So it ends up walking with the front limbs in a more straight configuration. It also changes the dimensions of the hind legs. And at the end, it reduces the maximum actuator torques over the walking cycle using this mechanical design. And it's the case that once we build the new design and we just measured the required torques, we saw quite a noticeable difference, so quite a noticeable improvement that was directly a function of this design, which was optimized through numerical simulation via a differentiable simulator. So this is still early work, but I think this is really exciting because it gives us the opportunity to think about co-design problems where at the same time you want to figure out how to optimize concurrently the brain or the control policy of a robot together with all sorts of design parameters, whether it's the structure of the load-bearing mechanical parts, essentially the bones. How do you make sure that they are sufficiently strong but as lightweight as possible? The selection and placement of actuators, maybe entirely new types of geometries for the joints, compliant feet, and so on and so forth. But this methodology now gives us a principled way of thinking about the way in which the mechanical design and the control policy can be optimized together in order to really improve the functional capabilities of future generations of robots. All right. If you have a bunch of data that you can use to formulate the optimization criterions, then basically this would take on the form of sort of model data mismatch. And I'll show you a few examples of the type of problems that we can formulate using this. So if you have just motion data that comes from motion capture, then you can start to ask these controllers to minimize the difference between the motion that's generated through simulation and the motion that you've captured from a real animal. And that allows us to create motion controllers for robots that are able to reproduce motions that we capture from real animals. If we try to provide demonstrations, so now the data is specifically as demonstrations of how a human might be solving a specific type of problem, then we can start to formulate learning by demonstration problems. So I'll show you a simple example here. What we see here is one of my students, Miguel. He is wearing a VR headset, and in this virtual reality environment, he's manipulating a towel. And what he is doing right now is he is just figuring out how to lay this towel flat on the table in front of it. And now, as a control problem, what you can try to do is you're just asking the behavior of a new type of towel to match the same type of behavior that we saw in the demonstration. Now, why is this important? It's important because for really complex problems, the objective is otherwise very difficult to formulate, right? Like we don't have a mathematical formulation of what fold a t-shirt neatly should look like. But if you provide a demonstration, then you can just say, well, do it like this, right? So this is basically the way in which we can use a simulation. And now the challenges are specifically for this towel that we're working with here is that as you're changing the proportions of the towel, the dynamics also change quite a bit. So the time constant, how long would it take it to get to the apex of a swing, for example, that's going to be very different as a function of the dimensions of the towel. So you have to be a little bit careful with how you scale the demonstration in time and space. But once you do that, basically this robot knows how to take a towel that is now longer than the one in the demonstration, and it basically just follows what Miguel did in the VR environment, figures out how to lay it flat. And if you change the size of the towel, now it's rather short, it's able to still use exactly the same demonstration, and the towel ends up flat on the table as we were hoping for. So if you combine this now with the ideas that we've seen in the self-supervised learning methodology, now you can basically create a robot that is able to take any towel and make sure it knows how to lay it flat on a table. And this is the first step towards more complicated actions like folding it or trying to figure out how to handle all sorts of other garments. All right, and last but not least, if we have data that comes from physical specimens and what we optimize over is model parameters, then we can solve problems that we call real to sim. I'll show you an example here. What we're seeing here on the right is a very complicated physical object. The fingers here were 3D printed in silicone, and you see that they're geometrically very complex. It's a high genus lattice structure. So together with the mechanical properties of the silicone, it creates a very dynamic physical system, maybe a future robot hand. And if you're trying to figure out, how do you import this into a simulator so that you can use it for motion planning and control? Well, on its own, that's actually a hard problem. And you would probably, if you want to use the right resolution for the spatial discretization of this object, you would need to have a lot of simulation elements in order to capture all the intricate geometry. So what we wanted to do is just have a very simple proxy simulation model, but we optimized its material parameters. So things like Young's modulus, Poisson's ratio, internal damping, and viscosity coefficients. And what we wanted is to automatically optimize for these parameters such that the overall behavior, basically the vibration modes, match the ones that we observe in the physical specimen. So that's what we see in the virtual model on the left, is a quite coarse simulation model that behaves in a way that quite accurately captures the behavior of the physical specimen. And then this model, basically, once you've imported it in your simulation environment, now you can use it for motion planning. This is something that we've done for this example. This is another soft robot. It's a crawling robot. This is the first step where we're just inducing some dynamics so that we are able to optimize the simulation model to match the physical specimen. And then in the simulation environment, we can design a gate. This is a kind of a similar setup as the one for the soft robot that we saw earlier on. It has motors that pull on cables, which then induce deformations. And because this model was tailored to the physical specimen, when you take the control policy and you apply it to the physical system, the behavior that you see actually matches the simulation environment quite well. So here we can see simulation versus real prototype. All right. So this concludes sort of the summary of the work that we do in simulation models and the various ways in which we use it. Oh no, sorry, I had a few more slides. I forgot I added these. So this is basically more pointing towards ongoing or future research directions. So we ask questions like, how far can simulation models take us? Is this the key to solving all sorts of manipulation problems or locomotion control problems, or will we hit a barrier at some point? Another important question is, where do the models come from anyway? So we have some sort of intermediate results for this question, right? We can have this real to sim step where we essentially do system identification, but for pretty complicated types of physical specimens. But at the end, there are all sorts of details, whether it's geometric or dynamic parameters that are perhaps still kind of difficult to automatically infer just when a robot sees a new object for the first time. And another very important question that we're also starting to tackle is how do we ensure safety and efficiency as we are learning control policies or dynamics models. And I wanted to show you some of the latest work that we've done here. So in everything I've talked about so far, we have a relatively traditional simulation model as a base for all of the work that we do. But what's important to note is that basically the simulation model, what it does is it looks at the current state of our simulation and some notion of control parameters, and it outputs the state of the system at the next time step. Now, in principle, this can be either a numerical or analytic simulator, or it could also just be a neural network that we learn from data that comes directly from the real world. So this is one of the hypotheses that we've tested in one of our recent projects. So basically, instead of assuming that we have a model or a simulation model, we just wanted to collect a whole bunch of data of a physical system, use all of that data to build a neural network, and then just use the neural network as the simulation model, that we then basically do exactly the same sort of operations that we've done on a numerical simulator. And the system that we've applied this to is an RC car. You can see it here. So this is a nice example because the RC car actually is quite complicated to model accurately, especially if you try to capture the drifting behaviors. You know, the mechanical design is actually quite complex. It has a lot of springs and damping elements. It's a very dynamic system. And what you see earlier on is that basically in the beginning of this project, we just want to provide random joystick signals, and we always just capture the way in which this RC car responds to the joystick systems. Once we have this, we take the Jacobians of the neural network that tells us how the output changes with respect to the inputs, and then we can start solving the same types of control problems that I showed you earlier that are based on a numerical simulator. And this ends up working surprisingly well. So I think it can be a very powerful tool that we plan to explore more in the future. So this car, without sort of knowing that it can drift or even what drifting is, it observes that it has these behaviors and it starts to leverage them as you're solving new types of control problems. All right, very good. So this is now the conclusion of sort of the technical part of the talk, but I wanted to just spend 2 more minutes to talk to you about ETH Zurich and some of the possibilities for joining us. So ETH Zurich, for those of you who maybe are not so familiar, it's one of the top institutions in mainland Europe. It's actually located kind of in the center of Europe. There are about 25,000 students that attend ETH and about, I think, 4,000 or 5,000 PhD students. So it's actually quite a research-heavy institution. I can spend a lot of time talking about how great ETH is and how beautiful Zurich is as a city to live in, but maybe you can also do a bit of research on your own if you're interested. And there's a big population of international students that attend ETH, and there are a few different ways in which you could also think about joining us if you're interested. So I've listed here some of the programs that are most relevant. Our department, which is the informatics or computer science department, has a summer research fellowship program. It's quite selective, but this is specifically aimed for undergrads, where basically you have the opportunity to spend 2 or 3 months embedded in one of the research labs in the computer science department, doing research together with one of the professors here and their research group. So I've listed here the URL for those who might want to find out more information about this program. For visiting graduate students, we have a robotics summer school. So this is particularly relevant for sort of the topics that I've talked about here. Again, a very competitive program, but a very nice opportunity to come and spend 2 months in the summer at ETH, working with one of the professors in specializing in robotics, and interacting also with a pretty diverse set of international students who come and join this program. For prospective master's students, we have a sort of traditional computer science master's program that you can apply to. We also have one that's specialized in robotics. It's called the Robotics Systems and Control, or RSC program. And again, links are here on this webpage. And last but not least, of course, we also take on PhD students from all over the world. What's sort of worth mentioning here on the doctoral studies side of things is that ETH has a decentralized admissions process for PhD students, which means that you would have to get directly in touch with the professors, figure out if there is a project that is a good fit for you and for the professor here. And if you do, you can basically start at any time of the year, as long as you have a master's degree. So a master's degree is required for PhDs at ETH. If you don't yet have a master's degree and you would like to do a PhD, we also have a direct doctorate program. You'll find more information here at the link, where basically you have to first do a master's degree at ETH with the understanding that if your GPA is high enough, then you're going to transition to a PhD afterwards. All right, so I will end here. Thank you so much for your attention, and I'm happy to take questions.
Awesome, Stelian. Thank you so much for the conversation today and sharing ETH Zurich.
I stopped sharing so that I'm able to.
And we have about 10
there
questions.
Are any
so
questions that come on
yeah,
chat, or
we're going to read off
the other way
for you. And we have questions in 2 different areas, both technical and educational pathways. So I'm going to hand it off to Leo Santos to go through the questions, and I'll also share the document.
Okay, great. Thank you, Rachel. Well, since you ended the talk talking about like educational pathways, I think I'll start with those questions. So the first one comes from an engineering mathematics undergrad student, and he's asking if you have some advice besides, for instance, the ETH student summer research fellowship, for him to engage in these kind of projects, maybe in their home university.
Well, I am not. I cannot talk in general about different universities and the various programs that they have. I guess we actually live in very exciting times as far as robotics goes, because over the past 5 years, we've seen really nice progress being made on the software side as well as on the hardware side of robotics. So you can now buy robots that are more accessible than ever before. Right, some of the quadrupedal robots that we're using for our research, for example, cost maybe as little as $2,000. Now, of course, that's quite a bit of money, but as far as robotics research goes, 10 years ago, you would probably spend, 100 or 200,000 on a platform. So it certainly is becoming much more approachable. And in addition, if you think, for example, of reinforcement learning, which is a tool that has really pushed the frontier in robotics research, well, this is something that anyone can get started with. You just need a computer. The better the specs, the less you will have to wait as you're doing training. But otherwise, it's very accessible. There are lots of resources online, ways to get started with reinforcement learning and really start building the basic understanding of some of the tools that are really useful in the world of robotics right now.
Oh, great, thank you. So following up with like another question about a PhD is, since in Europe PhD students usually apply to specific projects, how the flexibility to do research as a student in Europe compares to in US schools?
Again, it is a bit of a open-ended question. Probably every single project is different. Most universities are different. If you are thinking about joining ETH, the best thing to do is get in touch with the professors that you think might be a good supervisor given your interests, and then you learn the specifics of different projects, right? So at ETH in particular, we do have some amount of base funding, which means this is funding that can be used for entirely blue sky research, no deliverables, no specific targets that are imposed by maybe a funding partner. Some projects are funded through this mechanism. Others, of course, are funded through grants, and that's going to be a system that's very similar to the ones that you might know in the United States or in other parts of the world. So it really depends on which project you're interested in and what the funding mechanism is for this project.
That's wonderful, Stelian. This is Rachel again. I'm seeing some of the questions, and this is actually it. It's that they're coming from different backgrounds, different countries, and trying to navigate this space, and it gets really confusing, right? Like how do I, how do I apply? What are the methods and approaches when I'm applying to the U.S.? And I know in CMU, there's some faculty members that'll say, absolutely, reach out and contact me, and others are saying things like, nope, go through this. So what I hear you saying about ETH Zurich, and unfortunately for the scholars that are here with us today, it's the same thing. It's understanding the culture. So go to those websites, look at how they're trying to direct, and it does take a lot of work. And I know that it's overwhelming at times and confusing. There were two questions I thought were really interesting that I wanted to see if you'd share some of your experiences with us, and then we'll dive into the technical questions as well before we leave the educational pathways. So one was about from a student saying, are there seminal works or online resources that you really recommend for a student like me coming from universities that might have fewer resources or limited access? So if I'm coming specifically from a school or background where maybe I'll have industrial internships or co-ops and fewer research experiences, but this is what I'm really passionate about. Maybe I'm going online and I'm starting to search and doing things. Is there some guidance that you might be able to share there? So are there go-to resources or online sites that you're sharing with your students? Because you were saying that, while prices are coming down, there's also online resources and ways to join the scientific community. What are your thoughts there?
Yeah, I mean, this is still a very fast changing landscape in terms of the resources that are available. I would recommend that you follow the work done through NVIDIA. So NVIDIA has quite a big initiative in using simulation models for reinforcement learning. So if you search for something called Isaac Gym, for example, from NVIDIA, you're going to find the simulation environment and a suite of tools for reinforcement learning. This is a good starting point. Probably in a few weeks, there's going to be a new library also from NVIDIA called Orbit that will be even better. So if I sort of give you some links now, they might be outdated very soon, which is why I actually didn't list any of them. Again, it's such a fast.
It's so fast moving, right? I did
it's so
hear that.
fast moving.
Yeah.
It's so fast moving. But what I recommend is that you read some of the papers, right? So you can look, for example, at papers that come from my group or other groups at ETH or groups at CMU, because they all do list the tools that they've used.
Yep.
So if you like, I don't know, let's say legged robot research, right? Then just try to figure out where some of the newest papers are in this field and read them and see what kind of tools they are using. And then that's kind of the best way to stay up to date with the latest tools and the best developments.
Yeah, Stelian, that's wonderful. And I think for many of the students that are trying to engage, this is, what Stelian's saying about how fast moving things are, but don't let this be a barrier or something that is overwhelming. Stelian's group, the different groups at CMU, start reading, and the papers. There are some really cool tutorials out there also really about how to even approach reading a research paper. So the first time that you're going in, and most of the students that I'm working with, they find that the process of understanding the research papers can be overwhelming in its own, but you get started with it and you'll find that you pick up more and more. And so part of it is maybe challenging that it's so fast moving, but also it is really exciting as well. So I'm going to turn it back to
and what I would add to what you just said, Rachel, is that there is a skill in learning how to skim a paper for the information that you need.
Yes.
So there will be a lot of technical details that maybe are not so important. Then there might be some of the practical details that maybe in early stages you care about, which frameworks are used, which existing tools are used. And I agree, it's overwhelming in the beginning. But everyone who starts in research will have to do this in the beginning. So in fact, it's kind of the best practice. So yeah, just knowing how to extract the information that you need, being used to reading some of these papers in order to get the answers that you want.
Yeah.
This is also very important. It's much more important to have that skill than to go and ask a professor somewhere. You get the one answer, but then in a few months maybe that answer no longer works, and then
that really resonates, is learning how to learn. How do you personalize it for that? I will look for and try to drop in some resources. There's a really excellent tutorial that has like a practice sheet, but also a short video about approaching academic papers. And that's something that can stay with you. I know that Stelian only has a few more moments. I'll turn it back to Leo, and I'll answer some of the other chats that just live with you, and we can follow up and stay a little bit longer because Dr. Coros may have to leave. Okay.
Okay, yeah, since we're running out of time, I think I'll ask one of the technical questions, and then let's see. So we had this one. How are the interoceptive sensors different, or if they even are different, for those deformable robots, such as the crawler robot you showed earlier? And
yeah, I mean, these robots, I should call them prototypes, they actually have no sensing information. So everything that you saw is open loop execution of the control trajectories that we computed through simulation. So this is very far away from an intelligent sort of robot that is able to adapt to its environment or to other inputs. There are ways of embedding sensors into soft structures in order to estimate the way in which they deform. It gets a lot more complicated. It's sort of the reason why the field of soft robotics is still quite a bit behind more traditional robotic systems, the more traditional sort of metal robots that we've seen many times. So, you're pointing actually towards a very good research direction.
Okay, oh, great. So, well, this is a path you might explore if you're interested. And, well, I think we are, well, if you have one more minute for one question that I was curious about. Now that you said this, is but are we able nowadays to embed like stereoceptive sensors, like say a camera or something, and for the robot to, like, for instance, deform itself for, like, in real time to go through narrow passages, for example? Is this something that our people are working on? Because or it's just like something that, oh, you set an objective, oh, move forward, and then you optimize for this? Or can we do some kind of adaptation in real time?
No, I think this is not quite possible. So what I showed here is still early proof of concept that these differentiable simulators can enable motion planning and control for entirely soft robots, or for hybrid robots that have both rigid and compliant parts. Some of the questions that you're asking, how do you formulate objectives in a general setting? That remains hard. So it's kind of simple to say, I would like you to move forward by, this much in the next 2 seconds. If you have a much more complicated description of the environment and you want something very specific out of it, crawl through this thing and then turn to the left and so on, that becomes actually quite difficult to translate into a mathematical objective. And this is sort of why this line of learning from demonstration can, in principle, alleviate some of the challenges, right? So if you're able to show the robot what to do, then you don't have to write down the equations that are saying that. For soft robots in general, or actually for any robot in general, what you need is to have the perception capabilities. How do you know your own state or configuration? How do you know what the environment is like? You need to have, so that's kind of the perception side. You need to have the ability to plan your actions by predicting what might happen and choosing sort of the best action or a suitable action. And then you need to have the ability to act, so executing that action. And these are not entirely decoupled. If you want to do motion planning, you have to have a good representation of the environment. You also need to know what you can and cannot do, right? So basically the number of actuators or the design of the actuation system will tell you what the limitations are in terms of the space of motions you can produce. And so sometimes what you would like is not even possible given the actuators that you have. An example that I like to think about is an elephant trunk. An elephant trunk is an example that has inspired many roboticists in the field of soft robotics because it's so dexterous. It can do so many things, right? People say, oh yeah, it's so strong. It can lift an entire, 200 kilogram tree branch, but it can also just pick up one nut. And it's true, but it has 40,000 muscle fibers embedded inside of it. As a reference, the human body has maybe 500 muscles overall, right? So yes, there are examples in nature of soft systems that can do a lot, but they far exceed the mechanical complexity of the systems that we can build using the current actuation technologies and materials that we have available. So still lots of research to be done.
Okay, great. Well, thank you very much for joining us today.
My pleasure. Yeah.
So yeah, well, take care. Good luck
Thanks.
with your future endeavors.
Thank you very much, and good luck to everyone also with your journeys.
Thank you.
Okay, thanks everyone for joining. Bye bye.
Bye.